To calculate the divergence of this 2D vector field, we use the formula that is the del operator dot product with the vector field. The two-dimensional del operator is partial with respect to x, partial with respect to y, and we dot that with the components of the vector field, which are xy and y squared minus x squared. When we dot these two together, we're going to get a scalar function that depends on the xy ordered pair that we plug into it, and we're looking at the partial with respect to x of the first component of my vector field function. So this is the partial with respect to x of xy, and then to that we're going to add taking the partial with respect to y of the second component. And so let's evaluate these partials. Partial of xy with respect to x is just going to be y, and the partial of this component with respect to y will be 2y, so the divergence of this vector field is going to end up being 3y. In part B of this example, we're asked for which xy ordered pairs is the divergence going to be greater than 0, and we'll say that that's going to be true for all xy ordered pairs such that y is greater than 0. And here we have a 2D representation of this vector field, and we can kind of see this phenomenon taking place. Remember, when the divergence is greater than 0, we consider this to be an area where we see a decrease in density. It can also be thought of as a source area. And while this software has graphed all my vectors being the same length, we can still somewhat see that if we're looking at this positive y value in this area here, that we have vectors that are more traveling out of this region than into it. So this is an area where we'll see a decrease in density. But if we were to look at a point down here in the negative y region, we see that our vectors are flowing into that point, which is an indication that we'll see an increase in density.